Shokrieh from University of Washington, telling us about graphs and arithmetic geometry. The talk will be from 11 to 11:50, and we'll have 10 minutes for questions afterwards.
Thank you. Thanks for the invitation to speak here, and thanks everyone for joining the Zoom session. It's nice to see so many familiar faces and many faces that I would have liked to meet in person, hopefully at some point soon. Everything that I talk about, which is my work, is going to be joined with Robin de Jong at Leiden University. Feel free to raise hand or just unmute yourself if you have questions. I do not check the chat, but if there are questions in the chat that need my attention, I guess someone, maybe Chris, can bring it to my attention.
Yeah, I'll keep one.
Thank you. And one other thing is I miss the body language in human interaction. So I do maybe explain some things with my hand. If your technology allows, please keep my picture also on your screen. Okay. Maybe another warning is the work I'm going to talk about is at the intersection of many different fields, and I've tried to make it accessible to everyone. So if I'm failing at that, you're welcome to stop me and make me explain a little bit more. Okay, let me start by one claim, which says graphs are analogs of Riemann surfaces. So by a graph, I will be a little bit more clear what I mean, but think of an object which is graph-like. And Riemann surface, I don't really need the definition, but it's some kind of a donut. Maybe it has many holes and it has some extra structure. First of all, this is not a controversial claim. People in many different fields have already exploited this analogy. Say in geometric group theory, there is this notion of outer space, which is a funny name for the space of all graphs. The reason it's called outer space, people study outer automorphisms of the free group by studying its action on this space, the same way that people study mapping class group by studying the action on the Teichmüller space of Riemann surfaces, marked Riemann surfaces. And there are other buzzwords in these fields that relate Riemann surface situation to its analog for graphs. In probability theory, people have been thinking of graphs as Riemann surface-like objects, especially in the theory of random walks. They study Green's functions, especially in the case of infinite graphs, it gets you far. In fact, one very nice way of thinking of the object, do you see my cursor? The object on the left, which is a graph, is an analog of this. You can just think of these lines as being built from a very thin tubes instead of just line. So they have some thickness. And then if you think about it, these two pictures are essentially the same. This is just a thin version of this. And what probabilists sometimes do is to sort of guess certain properties of this by this sort of, one would say, simple analogy of thinking of lines as being tubes and maybe guess what Green's function should look like and then prove it concretely. And then maybe closer to my field of study and to this audience is the notion of tropical geometry. There is this notion of divisor theory, Riemann rock theory on graphs, theory of Jacobians, which I will talk about a little bit, Jacobi theory, which sort of formally are analogs of what people had studied since Riemann on Riemann surfaces. And often the proofs are still different. They're not sort of, the same proof doesn't apply to both situations. Anyway, so I will get back to this claim of graphs being analogs of Riemann surfaces soon, but let me say what I mean by graph. For me, a graph is, first of all, metric graph most of the time. And metric graph is an object that looks like this. Maybe a very quick way of defining it is a compact connected topological graph. By topological graph, I mean you start with a sort of one-dimensional simplicial complex and look at its geometric realization, but it also has a metric, and the metric is inner. What does that mean? So metric I suspect everyone knows what that means. Inner metric is a metric that the distance between 2 points is the length of the shortest path between those 2 points. So you can define a path between those points, and then you can compute the length. And in general, that length doesn't have to be equal to the metric of the metric space. And inner metric or length space is a space that satisfies this equality. Okay, but in short, I mean, it's you start with a graph-like object, and then you have some numbers, which signifies if you go from here to here, maybe you don't want to take the long path, you just want to take the shortest path, and it will be of length 1. One crucial difference is from the usual notion of graph theory graphs, like combinatorial graphs, is the fact that all points are created equal. So I allow myself to use points in between edges. Maybe you can model, if you want to tell a computer you have this graph, you can actually pick a few points. You can maybe you have to put these branch points, so this lower point and the top point, but maybe you can also pick middle of this left edge, middle of the right edge, and then tell your computer my data of metric graph is this. There are some arrows on these edges which I don't need for now, but you can ignore that. I hope everyone agrees this data would completely model this data. Is that okay? We call such a metric, such a weighted graph a model for the metric graph. But much more classically, even before graph theory, people were thinking of graphs modeling networks, electrical networks. The way that you should think of it is these lines now are made out of some copper wire, and the longer the wire is, the more resistance you have. So you can think of this this weighted graph or this metric graph as being modeled by some resistors. When you fix this model, you're sort of fixing the access points for this electrical network. The places that you can plug in a battery or measure the voltage or things like that.
Sorry, could you explain again why the weighted graph models the metric graph?
So I'm telling my computer that I have a line of length 4 by saying that it's length 2 plus 2. And I have these branch points. So unfortunately, I should have flipped this 90 degrees for the slide, but.
Okay, yeah, that's what was confusing me. Okay, sounds good.
Yeah, sorry. Any other questions?
How does correctness factor into how the weighted graph models the metric graph?
Sorry, I didn't catch the first word.
So in the second picture, I noticed there's the edges are directed.
Yes, I said ignore them. I mean,
okay.
it's useful in some of the, you can pick arbitrary arrows if you want. When you want to write concrete, you'll see sometimes it's good to put arrows, but the theory is independent of the arrows. I didn't need the arrows on these slides.
Okay, thanks.
Other questions? Okay, so let me start with this last point of view, the electrical network theory, and I will spend a few slides on this, and I will say things that are mostly standard, but at least 1 or 2 things that is not super standard, even if you have seen electrical network theory. So I start with a function with 3 variables. So I pick 3 points in my graph, x, y, and z. And I will do the following. I'm going to put a battery between y and z. This is not the usual battery you buy in a grocery store. It's a battery that fixes current, not voltage. So when you buy a battery, it says like 1.5 volts. But you can actually spend a few $100s and buy something that fixes the current going to the network. So I send 1 amp to point y. I remove 1 amp to from point z. And I fix my potential to be 0 at z. And what I will do, I will just go around my metric graph and measure the voltage between x and z. So in other words, z is 0, so I measure the voltage at x at all the points in my graph. Is that clear? So again, I have a battery between y and z, which fixes current, and I'm measuring voltage at various points x. And as I change x, y, and z, I have 3 choices, and I get different numbers. Okay, I call this conveniently the J function. It's kind of a sort of potential kernel to inverse Laplacian, but anyway, it doesn't matter too much. And I will define effective resistance between 2 points as being sort of the diagonal of this. I put x and x. So if you think about it in this graph, if I measure the voltage here, x is equal to y, then what's going to happen? I have current 1 going into y and exiting z, and I'm measuring the voltage at y. If you remember, V is equal to Ri, voltage is equal to resistance times current. Current is 1, so voltage should be equal to resistance. That's what so it makes sense from, if you know any sort of Kirchhoff laws stuff, it makes sense to call such a thing effective resistance between the 2 points. Okay? Maybe it's a good time to just remind people. Let me switch to my camera. What I mean is really what you probably know. In my first example, at 4, 1, 1, if this is my x and this is my y, if I ask what is effective resistance between x and y, well, you can use parallel law, 1 divided by 4 plus 1 divided by 1 plus 1 divided by 4, and you compute R, whatever that will give you. R is equal to R. Okay? This is 4, sorry. I'm not saying anything. Well, what I am doing is I'm taking this definition for the entire metric graph. That's probably not something that in a basic electrical network setup, you usually fix a model first and then do these things discretely. But now I have a continuous function essentially. All right, up to here, everything is sort of known. Maybe something that's new for most of the audience is this result of Chinberg and Rumbly, and some very related result due to Shokrieh. These are all arithmetic geometers. So you should start wondering why would they study what I'm talking about. Here's the result. There is a unique measure of total mass 1. I didn't say probability measure because this measure can be negative, such that this double integral will be maximized. Okay, I'll say more about this, but let me just say, why would anyone look at these kind of measures? By reminding you something again from physics, or some intuitive statement from physics, which is the following. If you have just a piece of metal, let's say in R2, it's a flat piece of metal, and you start putting electric charge of the same sign on this metal, let's say positive electric charge, what will happen is these electric charges don't like each other, they repel, right? And they would like to go to the boundary, probably intuitively you agree, they would like to go to the boundary to maximize their mutual distances from each other, right? Such a measure, so it's such a eventual configuration of electric charge is sort of, there is some distribution, you call it equilibrium measure. When things settle, these things go away, go to the corner. Maybe you even believe that sharper corners should have more charges. If you think about it, sharper corners, the mutual distances have a smaller contribution to the entire mutual distance. The way that electric charges would behave, probably they would like to make the total mutual distances maximum. They want to be as far away from each other as possible in total as a system, right? And then you can define a notion of capacity based on what is the total mutual distances when everything settles. That's a kind of measure of how much electric charge a piece of metal can hold, depending on its shape. And the notion of capacitor is very much related to that. So I was, in a way, I'm going back to my slides now. The total mutual distances is this double integral that I had. effective resistance gives you a notion of distance on the graph. I'm looking at total mutual distances, and I'm looking for a configuration, equilibrium configuration nu, which is my unique measure of total mass 1, that makes total mutual distances maximum. Okay, I'm looking at capacity of the graph in some sense, where the distance the distance is measured by effective resistance. It's a very natural thing to do. Okay, not only this, Chinberg and Rumbly actually do a nice computation and say what this equilibrium measure is. The equilibrium measure, I don't really need all the details of this, but I will need essentially this definition of Fe. The measure that maximizes this energy is, it has a discrete part in red, which I don't want to dwell on too much. It's number of directions at any point that at that point -2. So it's this discrete part is 0 most of the time, because most points on graph have only 2 directions. You will pick up a delta measure whenever your degree is not 2. But then there is a continuous part, which is more interesting. You start with the Lebesgue measure on, so any line in the graph is just like an interval. So you have a Lebesgue measure for that, where the total Lebesgue measure is the length of that interval. What I will do, I will just rescale that length by something which is f of e. It's called Foster's coefficient, and it has a very interesting interpretation. So one interpretation, which is easy for me to state, is 1 minus effective resistance across the endpoints divided by the length of that edge. That's a self-contained description. Maybe another one which is more interesting and brings in probability is that it's probability of a random edge, a probability of a given edge, the edge E, not being in a uniform random spanning tree. Okay, so there's a interesting theory of random spanning trees. You can learn in any interesting literature, maybe Lyons and Perez's book is a very nice place to start. And these numbers have been studied. So the equilibrium measure for maximizing this energy, somehow realizing the capacity is up to some discrete part, is very much related to random spanning trees.
So here the R of E minus and E plus is just like the using the Kirchhoff rule.
It's the effective resistance across the endpoints.
Yeah, like so you account for all the other paths going from E minus and E plus, which depend on the lengths of the paths. Is that correct?
Yeah, so it's the Kirchhoff rule, like in the example I had in my write-up, the top and bottom of the thing, that's R of all these edges, across all these edges, but each edge will be divided by the length. So
I see. Yeah.
Yeah.
Sounds good.
Other questions? I see some things are happening on the chat, but I'm not checking it. So I'm relying on Chris to tell me if I have to answer anything.
I have a question about the function R. So are we only talking about the effective resistant function for circuits, or are there like other general properties? Are we talking about general metrics for R, or?
R is just the effective resistance. It does give a metric.
Okay.
It is true that if you fix any other metric, you can ask the same question. But the two natural metrics that you can consider, one of them is just the original metric. It was a metric space. You could use the original metric and ask the same question. It turns out this metric is more interesting because it relates to harmonic analysis, sort of Laplacians. And, yeah, it's a more natural thing, at least from the perspective of number theory.
Okay, that's cool.
Other questions? Okay, so in fact, I don't really care about this equilibrium measure in this talk, but I do care a lot about the value of the maximum, the capacity of the graph. So this measure will give you some maximum, and I will call that tau capacity. It's the maximum of the energy functional. And okay, so I've given you a definition. It's not very computational. Here is another definition. It's a lemma that you can show this value of the capacity. you can compute it by the following method. You look at the function f, fix a point q. It turns out your final answer will be independent of the q. And then for any other point in the graph, compute the effective resistance between the given point x to that q. That gives you a function on the graph. And by treating all these lines in the graph as being intervals, you can take a derivative. Look at the derivative of that, square that, and integrate over the entire graph, and you get this tau, this capacity. It's a lemma, not so difficult. This is, I mean, I've written it in an easy way, but you could say it more fancily. This is sort of the Dirichlet product of f with itself. But don't worry about it. Okay, this is a satisfactory thing. If I give you a metric graph, you can compute this tau using this formula. But in fact, it would be nice to have something that computer can compute. So let's get rid of this integral. And there is a proposition or lemma that sort of, at least implicitly, has already appeared in a work of yet another arithmetic geometer. The Shokrieh Zubair was Zubair was a student of Rumbly, another arithmetic geometer. And for some reason, he studied this quantity as well. In fact, his PhD thesis was about tau. It's 250 pages studying properties of tau. And in the particular format I'm writing here, it's a result of ours, and the proof is slightly different. But anyway, you can compute this tau very concretely. So again, I don't care about exactly what, I mean, this is effective resistance function. For you fix a model for any edge, you compute a bunch of effective resistances. This f of e was this Foster's coefficient, which was related to probability or effective resistance. All I want you to notice is that this is very easy to compute using linear algebra. So all these quantities, effective resistances, are linear algebraic quantities you can compute if you know the Laplacian of the graph, the combinatorial Laplacian of the graph. Okay, so the take-home message from this slide is there is this notion of capacity. It can be computed, and in fact, it can be computed really fast. And maybe I will end this discussion by saying that Rumbly also had this inequality that tau is at most 1/4 total length of the graph. So just add all the edge lengths of all the edges that you see, divided by 4, and equality holds if and only if the graph is a tree. It's contractible. I'll get back to all these points soon. Any questions about this? I'm going to move to something seemingly different about graphs. I'm done with electrical networks. No questions. Okay, let me switch gears and talk about geometry of graphs. This is more related to tropical geometry or non-Archimedean geometry, but the definition is very basic. For any metric graph, you can define something called its Jacobian. And this is, again, by analogy. You might have heard curves or Riemann surfaces also have some object called Jacobians attached to them. In this case, if you have a metric graph of genus G, by genus, I mean rank of the fundamental group, or very concretely, if you fix a model for your graph, just count the number of edges minus number of vertices plus 1. So any graph, there is this integer that you can attach to, and I'm saying any metric graph has a G-dimensional real torus attached to it, and it's more than that, it has a polarization. Okay, so let me say what this object is in very concrete terms. You look at integer valued flows, and you look at real valued flows on your graph. For this, let me actually change again to my camera. Now I put arrows because I want to put some numbers which are directional. Forget about the lengths. In fact, for now, integer valued and real valued flows has nothing to do with lengths. I'm going to put maybe a number 2 here, -1 here, and -1 here. I claim this assignment of numbers is kind of, it gives you a flow, because at any point, the incoming flow and outgoing flow is going to be equal. It's pretty clear at any point along the way. 2 is coming in, 2 is going out. There is no problem on the left. At here, 2 is coming in, but then there is a -1 coming in. In other words, 1 is going out, 1 is going out. So there is some sort of a conservation at every point. You call such a thing a flow. Okay, and then you have integer valued flows, meaning that the numbers that I wrote down are integers, and you can have real valued flows. Maybe pi plus e comes down, e goes up, pi goes up. That's a real valued flow, right? Let me remind you that, first of all, the space of all real valued flows is going to be a vector space, because you can add or subtract flows, you get flows, and you can scale them, you can multiply all these numbers by square root of 2, and you still have a flow. It's a vector space, and space of all integer valued flows is not a vector space, but it's a sort of Z module inside the vector space. It's a lattice inside the vector space. Okay, but let me also emphasize that in everything I'm saying here, I forgot the length information. I'm not really remembering that the length of the left one was 4, 1, 4, or anything like that. These spaces are not taking into account the lengths, but that's where the polarization comes in. Polarization will remember those extra data. Let me go back to my slides. Okay. So this Jacobian that I want to be a real torus, I think you already can guess what I'm going to do. I have a vector space of real valued flows. I have a lattice inside it. That sounds a lot like a torus. I'm going to look at the quotient of the vector space by this lattice, and I'm going to do an example in a moment. Again, I remind you that I was forgetting the length data, and I want to somewhat encode that. What I'm going to do, I take this polarization to be the cycle intersection pairing. So what do I mean by that? The space of flows can be generated by cycles. If you just pick a cycle in your graph, a simple closed path, you can put a flow which is just circulating on that cycle, right? Is that clear? And it's a basic fact that all flows are combinations of these basic flows. You can make any flow on the graph if you just know the cycle flows on the graph. And this is true both in the real valued space and integer valued space. So they give a generating set for the lattice, which at the same time almost trivially will give you the vector space basis. So what is cycle intersection pairing? Now I want you to see my picture if you're just looking at the slide. If you have two cycles, you can define a pairing between them, a product between them, where remembers the length of their intersection. That's cycle intersection. So if the two cycles are disjoint, cycle 1 times cycle 2 is going to be 0. If the two cycles have some intersection, you remember the length of their intersection. Okay, this is cycle intersection pairing on. In some way, it's not clear, but in some mysterious way, I'm remembering some length data anyway, right? It's not super clear whether I'm remembering every length data, but that's a whole different interesting question that relates to something else that I don't want to talk about. Any question about Jacobians?
Is this pairing degenerate, non-degenerate?
It's perfect pairing. So it's positive, definite, symmetric. Yeah, quite bilinear form, positive, definite.
There's a question from the audience. If the cycles are oppositely oriented on their intersection, is there cancellation?
Yes, so it's, I have done all these things in terms of the homology first, which I didn't want to talk about. And these things are all, if you want to write them, well, let me do the next slide with the example, yes, if in your orientation that you have fixed, you don't need an orientation to define everything I defined. But if you are thinking, as I will in the next slide, as cycles being oriented, then yes, you have cancellations too. So you have E times E is 1, E times minus E is minus 1. So you have signed computation. Let me do maybe the next example, and then I will come back. So let's look at the same example we have been looking at. I'm forgetting the length data for now. The cycles in this graph are E1 minus E3, or some basic cycles in this graph are E1 minus E3, so it's the outer cycle. I'm coming down on the left, going up on the right. That's this point. I have the zero flow, put 0 everywhere. If I put 1 and minus 1, I have this flow, this simple cycle. I have E1 minus E2 come down here, go up there. And I have E2 minus E3. That's kind of redundant, but let me say it. I have these basic vectors inside the space of flows. The way that I've drawn this is actually remembering some angles. And angles are related to dot products. And like E1 minus E2 dot E1 minus E3. So the E1 minus E2 cycle and E1 minus E3 cycle have this E1 in common. And what I will do, I will remember the length of E1 squared. Sorry, length of E1, not squared. Length of E1 will be the dot product between this vector and this vector. Okay, and then use the cosine formula to compute the angle between the two if you have the dot product and you have the lengths. I guess the way that I've drawn this picture, I'm assuming all the edge lengths are now 1, 1, 1, 1, then I get 60-degree angles here. Is that clear? And I think it's now also clear that you can have minus E1 minus this element, E1 minus E2. So E2 minus E3 is where my cursor is now. And then, yes, you have angles more than 90 degrees. So this product can have negative values too. Is that okay? Did I answer the question in the chat? Okay, so the torus that I'm going to think about is this. This is the fundamental domain for the torus. Of course, you can make identification of opposite edges, and you can draw it as a torus if you like. But this is, just remember, this is not kind of only a torus. There is also a bilinear form. Maybe you can think of the tangent at the origin, and you're fixing a bilinear form on the tangent space, or universal cover, or whatever. I mean, you can describe this product as some extra information in various ways. I called it polarization. And I must say, I noticed in the next talk, this notion of sort of maybe not Jacobians, but tropical abelian varieties comes into the talk. And I suspect this should be relevant explanation for what is a polarized tropical abelian variety. Okay.
Do you mind explaining more minute, like what the where you got those angles from again? Because I understood the. It seems like, so you said you got like E1 was the product, but then how did that E1 turn into a 60-degree angle?
Yeah, let me do that with a piece of paper. So you have E1 minus E2, and this is one, E1, E2, E3. And you have E1 minus E3, for example. Their product will remember the length of E1, because the intersection of these two cycles is just E1. And let's assume that length is 1. Then you have the cosine of theta is the product of, let's call this C1, let's call this C2. It's product of C1 and C2 divided by length of C1, length of C2. And if I'm assuming all the edge lengths are equal to 1, then I'm looking at 1 divided by 2, and that will be cosine of 60 degrees, right?
Okay, cool, interesting.
If you change edge length, this computation is gonna sort of, your torus is gonna be tilted. The lattice is gonna be, the angles are gonna change. So somehow the angles will remember the edge lengths. In fact, I mean, there is something called tropical Torelli theorem that it says you can essentially reconstruct a graph from this data, but that's the thing I said I don't want to talk about. I'll be happy to chat later. Other questions? Okay, now I'm going to define a function on this space of flows, which does the following rather useful thing. If you give me a flow, I'm going to find the closest integer flow, and I will remember the distance squared from that integer flow. Okay, so I'm looking at the product of the x minus lambda, where lambda is an integer flow, and I'm looking at finding the closest integer flow. It's the closest vector problem in lattice theory. So you have an element of the vector space, you're finding the closest points in the lattice to that space, to that point, and you're remembering how far you are. You can think of this as like a quantization problem. Your data is in a vector space, and your digital data, the thing that you want to feed to your computer, is this discrete data of the lattice. And this is like the error for your quantization. Is that clear? For some reason, I call it absolute value of theta, but that comes because of the arithmetic geometry context. One observation is that this function is periodic with respect to the lattice. Is that clear? Let me once again switch. I didn't intend to switch so many times, but now that I'm used to it, I'll do it. So if you have in this previous picture, you have this lattice. Like given an element of the vector space here, maybe this is the origin. This function theta will remember the closest lattice point, which is maybe this, and remember this distance squared. And the periodicity is that if you give me a point which is a shift of this with respect with a lattice element, then the output will be again the same. That's the periodicity statement that I was saying, right? Any question about this? All right, so it's a periodic function. It descends to the Jacobian. Remember, my Jacobian was just the space of lattices modulo the space of flows modulo the integer flows. If it's a periodic function, in fact, I have a function on the Jacobian now. It's a real valued function. And what I can do is I can just integrate this function on the Jacobian with respect to probability Haar measure. So there is a natural measure on any compact Hausdorff compact group called Haar measure. I will normalize it by saying that the total measure is 1, and I'm computing this number. If you know Voronoi decompositions for lattices, so a Voronoi cell is the space of the set of all points that are closest, let's say, to the origin. What I'm really doing, I'm just computing the second moment of that polytope. I'm looking at z.z, and I'm integrating over that polytope. This is mostly for people that know Voronoi decompositions, but I've technically given you the definition. And in that sense, it's really a quantity that's been studied before. It's a quantity that in the quantizer interpretation, it's computing the mean squared error for the quantization. So it's saying on average, what's the error for the quantizer. Okay. So now I have yet another quantity. You give me a metric graph, I go through all the machinery I introduced in the past few slides, and I compute another number. And remember, in the previous discussion, I had yet another number called capacity of the metric graph. And I can now present the first result. These two numbers are related they're very different animals. I mean, this comes from the geometry, this comes from potential theory or electrical networks, and surprisingly, they have a very simple relationship between them. So this capacity up to some constants, the capacity plus this moment of the Voronoi is just the total length. It's a linear relation between them. Okay, so a few remarks. First of all, the proof of this, well, maybe the first question is, how would you even guess such a thing is true? I'll address it at the end of this slide, but the proof of this actually goes through a range of different topics, which there are many experts in the audience. We do need probability theory. I already mentioned some connections with random spanning trees. We do need, of course, combinatorics. We're doing graph theory, convex geometry. We're studying Voronoi polytopes, for example, and electrical networks definition. And it's kind of a elementary proof, but rather surprising that it works. Let me just, as a consequence, let me tell you, tau was computable. Remember, there was this formula that I said you don't have to memorize it, just remember it, you can compute it fast. Now you can compute I, because the total length is easy, you can compute tau, so you can compute I from this formula. And that's already somewhat surprising. I, for a general lattice, is expected to be very hard to compute. It should be worse than Shokrieh hard. And in fact, even for the lattices we consider, a lot of computational questions are difficult. For example, the number of vertices of the Voronoi cell of our lattice is Shokrieh hard to compute. And there were good reasons that people would, I think it's still open, the difficulty of computation of moment of a general lattice is still open. And there was some attempt to try to prove it using R lattices. Somehow they bring in combinatorics and allow you to use usual reductions in computer science. And so, I mean, from computational complexity perspective was also surprising. Let me make another point. In a way, this is making Rumbly's inequality into equality. We are giving the error term. Rumbly was saying tau is less than or equal to 1/4 L. And we are saying the difference between the two is actually this I. We are computing the error term in terms of the moment of the associated Voronoi of the flow space. And this number is bigger than or equal to 0 by construction. It's moment, second moment. And it's 0 precisely when Jacobian, the lattice is just a point. And if you think about it, that means you don't have a flow in your graph, which means your graph doesn't have a cycle, which means it's a. Okay, so this is not the easiest proof of Rumbly's inequality, but it gives that as a consequence, and it gives the error term. And the way that we came up with this conjecture before we have the proof is actually by analogy with Riemann surfaces. So there's a remarkable result due to Robert Wilms on Falting's delta invariant, and somehow with degeneration, we expect that such a thing should be true. And then the proof of Robert is very analytic, and it wouldn't carry on to our situation. We had to do things by hand. Okay. And in the remaining few minutes, I want to say a few things. How is this? What the second part of my title was arithmetic geometry. How is this related to any number theory or arithmetic geometry? Okay, and it will be for some time philosophical. In my last slide, I'll say a result which puts this into a context. Any question before I move on to arithmetic geometry? Well, it's not going to be serious arithmetic geometry, but let me go back to the question of graphs versus Riemann surfaces. In the first slide, I said they are sort of morally analogs. I want to be more precise. How is it that graphs actually, the sort of qualitative analogy is not good enough for our application? I want a more robust connection. And for that, let's go back to the context of sort of very classical geometry. If you have a variety over C, think of it as collection of zero sets of zero set of a collection of polynomials. And in fact, for this slide and for some time, it's good enough to think about polynomial 0 in one variable. So you have the 0 polynomial in C square bracket Z. And you look at the 0 set of that, 0 equal to 0. Well, 0 equal to 0 is always true. So the 0 set will be the complex numbers. But algebraic geometry tells you that the topology that you should put on that set is Zariski topology, meaning that you should consider the 0 sets of more polynomials. So closed sets in Zariski topology, in the running example we have, the complex plane, the closed sets are going to be finite points, finite set of points, or the entire thing or empty set. Open sets will be co-finite sets. And of course, that's ridiculous. You don't want to study that space. You don't want to study the complex analysis course using this silly topology. You don't want to use Zariski topology to do analysis. So what you do in a complex analysis course, you switch to, you remember C has absolute value and use that absolute value to give analytic constructions. If you do it with A1, which is the 0 polynomial situation, you actually, if you run this program, you get the complex plane with the usual topology, analytic topology. If you do it with curves, you get what is called Riemann surfaces. And if you do it with abelian varieties, you get complex tori. There are fields out there that are not like complex numbers. There are so-called non-Archimedean fields. They have absolute values, but the absolute value is actually the usual triangle inequality is stronger. It's not absolute value of x plus y is sum of absolute value of x, sum of absolute value of y, but rather just the maximum. And these are very common fields out there. So number theorists would probably think of p-adic numbers and its extensions. Geometers might think of formal Laurent series. If you are neither, you can just know the fact that almost all fields are non-Archimedean. So somehow there is a theorem due to Ostrovsky, and then later on follows from a work of Gelfand and Mazur that says any complete Archimedean field is essentially just R or C. But there are many, many, many fields out there that are. So somehow the common, a random field in the street is going to be non-Archimedean, and it's reasonable to ask, how would you do the program up there? If you start with a variety, you can look at the 0 sets with the Zariski topology. You might not like that for obvious reasons. You might want to use the absolute value and come up with a new topology that you can do analysis. And the sad thing is that you will always get a totally disconnected space, a type of space that's not good for analysis when you do exactly what you did for C. And then I'm going to show you some pictures. Berkovich realized there is a way to canonically add points to this totally disconnected space and make it a very nice space topologically, which is ready to do analysis. Okay, so I'm not going to tell you how he does it, but I'll show you some pictures. Berkovich A1. So you have this totally disconnected space. Think of it as these dots at the bottom of this tree. And then Berkovich creates all these extra points and somehow makes a tree out of them. This is a schematic picture, which I stole from Matthias Johnson's paper. So you get a tree. All I want to say is that when you run the machinery of Berkovich, you get a tree. Okay? And similarly, Riemann surfaces locally look like a piece of complex plane. If you think about curves now over non-Archimedean fields, they locally look like a tree because complex plane has turned into a tree. Things that are locally like a tree globally are going to be graphs. So somehow graphs are Riemann surfaces in some sense, except that they're not Riemann surfaces over C, they're Riemann surfaces over non-Archimedean fields. Okay, and that gives you a technology to take a question over non-Archimedean fields to graph theory, which is sort of source of a lot of interesting combinatorics. If you run this program for curves, as I said, you get graphs, and it turns out any graph actually appears as a fundamental sort of part of this skeleton, this dumbbell graph. Any graph appears inside a curve in this setup, in this situation. And similarly, for abelian varieties, you get real tori. So let me go back and say what I was really doing in the first part of my talk. When I was doing electrical network theory, I was actually doing something, potential theory over analytic curves, over non-Archimedean Riemann surfaces. It's sort of a fancy way of putting the initial computation. And any curve has a Jacobian. You can look at this, their analytic Berkovichy stuff. And as I said, curves give you graphs. Abelian varieties give you real tori. And I was really studying the moment of the Jacobian of the metric graph is a quantity attached to the Jacobian of the curve. Okay. All right. So let me end by saying that summarizing how the result fits into what a number theorist might care about. If you start with a abelian variety, I don't want to dwell too much on these terms. It's a discrete math conference. I'll be happy to chat later. But let's say elliptic curve. You probably have heard about elliptic curve, or at least Weierstrass equation. Y squared is equal to x3 plus x plus 1. Just take a very concrete thing. These are called abelian varieties. There are two numbers that you can attach to this data, principally polarized abelian variety, and they capture the complexity, how complex these things are. One of them is due to faultings. The other one is extension of the work of Néron and Tate. And with Robin de Jong, we had this other paper that proves that these two quantities are related in this way. So the faultings height, the complexity number 1, is equal to complexity number 2 plus some local data. And the local data is I invariant of all these analytic pictures. So for n at place at infinity, for the Archimedean place, you get a complex torus. You can compute a number from that. For any prime number, you get a real torus, and you can compute this moment for it. And I was essentially telling you how to compute these moments in terms of capacity theory. Okay, so the last slide is, first of all, the proof of this theorem is actually Berkovich. It's not combinatorics, but what I wanted to emphasize is that for Jacobians, I was telling you how to compute these numbers in terms of capacities. And probably you don't care much about these things. The result extends something that people knew for elliptic curves, and partial results in this direction were due to Bost and Hendry and Althusser and Wagner and some other people. And yeah, it gives some concrete results in terms for faultings height in terms of local decomposition, which I'll be happy to chat later. Anyway, thanks for your attention.
Okay, thanks for a great talk. Let's thank our speaker. So are there any